something is amiss in our cognizance of the universe. Cosmology is moving toward a basic crossroads, wrestling with one of its most essential issues. How rapidly is the universe expanding? For over 10 years, two different measurement methods have been at odds. Observations of the current-day universe typically show that the rate of expansion, known as the Hubble constant, is around 9% faster than what is predicted based on data from the early universe. Researchers had hoped that the James Webb Space Telescope, the most advanced telescope ever made, would help resolve this issue conclusively. However, consensus has yet to emerge as the telescope's remarkable, novel observations have further solidified the discrepancy, representing a potential challenge to the established cosmological model. Now, the need for new physics to either modify or completely replace the 40-year-old theory is under serious discussion. An exhilarating and captivating possibility is that we are overlooking some aspect of the universe. Join us as we delve into how the new ultra-deep images from James Webb have recently confirmed that there is something fundamentally flawed in our understanding of the universe. Our universe began with a bang, the Big Bang. Energy, mass, and space appeared immediately thereafter. The young universe formed a growing plasma, a mixture of matter and antimatter particles that emerged and annihilated each other as they collided. Left unchecked, the matter and antimatter in this plasma would have destroyed each other completely. However, scientists believe an unknown anomaly allowed more matter to form than antimatter, thus saving the universe from immediate destruction. Gravity then compressed this plasma, heating the matter so much that sound waves, known as baryon acoustic oscillations, traveled through the medium at roughly half the speed of light. Simultaneously, the dense energy content of the early universe expanded spacetime, pushing a small fraction of matter safely away from the heat. As the universe expanded like a balloon, the standard story suggests that ordinary matter, which interacts with light, began to cluster around invisible dark matter, forming the first galaxies connected by a massive cosmic web. As the universe's contents spread, its energy density, and consequently its rate of expansion, decreased. Yet, around 5 billion years ago, galaxies began retreating faster, driven by the mysterious force known as dark energy. The most straightforward and widely accepted explanation for dark energy is that it functions as a cosmological constant, a uniform force that remains constant across both space and time, woven into the fabric of expanding spacetime. Named lambda, by Einstein in his theory of general relativity, dark energy density remains unchanged as the universe grows, while the density of ordinary matter drops. Eventually, dark energy became the dominant contributor to the universe's expansion. When combined with ordinary matter and dark matter, the energy densities of each set an upper limit on the universe's expansion speed. These components form the core of the lambda cold dark matter, lambda CDM, model, which describes the evolution of the universe and predicts its eventual fate, a heat death known as the Big Freeze. Many of this model's predictions have been proven highly accurate. However, this is where the trouble begins. Despite extensive research, astronomers are still unaware of the true nature of dark matter and dark energy. As Afra Love, a cosmology professor at University College London involved with dark energy galaxy surveys, states, most scientists agree that the universe's current makeup is around 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing truth is that we still don't understand the latter too. An even greater challenge to the lambda CDM model, however, is the growing issue known as the Hubble tension. Depending on the method used, measurements of the universe's expansion rate yield conflicting results. The divergence is critical to the point that it has become a pressing issue in cosmology. Measurements derived from observing the early universe suggest it is expanding far faster than predicted by the lambda CDM model. These methods have undergone extensive testing and validation through various observations. As Nobel Prize-winning astrophysicist Adam Rees, who led the team responsible for the latest James Webb measurement, put it, the only explanation for the discrepancy between the two approaches is that our current model is likely missing something. Estimating the universe's expansion involves more than just using a radar gun. One primary method examines the cosmic microwave background, CMB. The universe's first light emitted around 380,000 years after the Big Bang. This imprint is visible across the entire sky and has been mapped to infer the Hubble constant with less than 1% uncertainty. Between 2009 and 2013, the European Space Agency's Planck satellite produced a detailed map of the CMB. In this cosmic snapshot, the universe is nearly uniform, but slight variations in temperature, where matter is denser or sparser, mark the points where baryon acoustic oscillations left their imprint. This soap-bubbled structure expanded into the cosmic web, a network of filaments connecting galaxies at their intersections. By studying these waves, cosmologists inferred the amounts of ordinary matter, dark matter, and the cosmological constant or dark energy, calculating the Hubble constant to about 67 kilometers per second per megaparsec. To put this into perspective, if a galaxy is 1 megaparsec away, it will retreat at a speed of 67 kilometers per second. At a distance of 20 megaparsecs, this recession grows to 1,340 kilometers per second, continuing to scale. If a galaxy is farther than 4,175 megaparsecs away, it will retreat faster than the speed of light. Another method to measure this expansion rate involves variable stars, pulsating stars whose outer layers expand and contract as they absorb and release radiation, causing them to blink in a predictable pattern. This behavior, discovered in 1912 by astronomer Henrietta Swan Leavitt, allows astronomers to determine the absolute brightness of these stars, which can then be used to measure their distance. The Cepheid-based technique, known as the cosmic distance ladder, was a pivotal discovery that allowed astronomers to measure vast distances. The first rung of the ladder is built by measuring nearby Cepheids and cross-checking their distances. Following this, the distances of more distant stars and galaxies are determined by observing how much their light has been stretched, redshifted, as the universe expands. By comparing this data, cosmologists calculate the Hubble constant. In 2019, Rees and his team used this method by pointing the Hubble Space Telescope at the Milky Way's closest neighbor, the Large Magellanic Cloud. Their results were groundbreaking, showing a much higher expansion rate of 74 kilometers per second per megaparsec, compared to Planck's measurements. However, Planck's results were limited by its lack of precision in crowded regions of space, where distant Cepheids blurred with neighboring stars. Some dissenting cosmologists argued that this discrepancy could have been due to measurement error. But when the James Webb Space Telescope launched in December 2021, it was expected to resolve, or perhaps confirm, this discrepancy. With its 6.5-meter wide mirror, over 3 times the size of Hubble's, and superior infrared capabilities, James Webb observed fainter objects and detected a broader range of wavelengths. The debate surrounding the Hubble tension underscores a larger issue in cosmology: our incomplete understanding of the universe's most fundamental forces and components. Some physicists propose that dark energy may not be a cosmological constant at all but rather a dynamic field that changes over time, known as quintessence. If this were true, the evolving nature of dark energy could explain some of the discrepancies in measurements. Others suggest that dark matter, long thought to interact only gravitationally, might have more complex properties that subtly influence cosmic structures and expansion. Alternatively, some theories challenge the foundational framework of general relativity itself, proposing modifications to Einstein's equations that govern the behavior of spacetime on large scales. While these theories are compelling, they remain speculative. Testing such hypotheses requires new observational data, advanced simulations, and, potentially, a paradigm shift in how we conceptualize the universe. The James Webb Space Telescope, with its unprecedented capabilities, has already provided hints that our current model might be incomplete. Its deep-field images reveal galaxies that appear more massive, luminous, and mature than expected at their observed distances, potentially challenging the timeline of galaxy formation in the Lambda CDM model. Moreover, Webb's observations of star clusters, intergalactic gas, and distant supernovae have refined measurements of cosmic distances, further confirming the tensions in Hubble constant estimates. If the tension persists, it could signal that we are on the brink of a scientific revolution, much like the one that followed the discovery of dark energy in the late 1990s. As cosmologists grapple with these challenges, the stakes are high. Resolving the Hubble tension isn't just about refining our measurements, it's about understanding the very fabric of the universe and our place within it. Whether the answer lies in new physics, observational breakthroughs, or a deeper reinterpretation of existing data, one thing is clear: we are witnessing a pivotal moment in our quest to decode the cosmos. For now, the universe keeps its secrets, but with tools like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope, the next few years promise to be transformative. The mysteries of dark matter, dark energy, and the true nature of the cosmos may finally come into focus, providing answers that could reshape our understanding of existence itself. Material science. The main speculation is that dark energy's behavior has changed over time. If dark energy was once stronger and gradually faded, it would cause the universe to appear smaller in its earlier stages, which would result in a faster expansion rate today. Other possibilities include the presence of two kinds of dark energy or dark matter interacting with light. However, these hypotheses present challenges that many cosmologists are reluctant to embrace, minus any additional proof. James Webb's discoveries are not just testing how we might interpret dark energy and dark matter. They are reshaping our thoughts about universe development. By looking further back in time than ever before, the telescope has uncovered galaxies that were significantly larger and more advanced than the Standard Model had anticipated, forming only 300 million years after the Big Bang. Early galaxies, which should have been made of young, hot stars, were found to have heavy elements and even very massive black holes at their centers, features that tested the traditional model of universe development. These findings have intensified the debate within cosmology, suggesting that the processes governing galaxy formation may have been faster and more efficient than previously thought. As well as addressing these major mysteries, James Webb's discoveries have also expanded the riddle surrounding dark matter and dark energy. Despite being the dominant components of the universe, both remain poorly understood. While dark matter interacts gravitationally, its exact nature is still unclear, prompting ongoing investigation into its detection. Similarly, dark energy is responsible for the accelerated expansion of the universe, but discrepancies such as the Hubble tension raise the possibility that dark energy's properties are not uniform across spacetime. Alternative hypotheses suggest dynamic forms of dark energy that could evolve over time, affecting the expansion rate differently at different stages of the universe's history. To solve these mysteries, astronomers will need both advanced observational tools, like the James Webb Space Telescope, and theoretical frameworks that can integrate the new data without discarding the successes of current models. The implications of Webb's discoveries extend far beyond cosmology, influencing broader astrophysical questions, including the origins of life and the conditions necessary for life to emerge on other planets. By studying distant worlds, astronomers hope to uncover clues about how Earth-like planets might evolve around different stars, offering potential insights into the prevalence and diversity of life in the universe. Looking forward, the James Webb Space Telescope promises to continue pushing the boundaries of our cosmic understanding. Its unparalleled sensitivity and resolution will allow astronomers to study the atmospheres of exoplanets, map galaxies with greater detail, and examine the earliest epochs of cosmic history with unmatched accuracy. These efforts will not only expand our understanding of the universe's past but also pave the way for groundbreaking discoveries that could revolutionize our perception of physics, space science, and our place in the universe. As Webb embarks on its operational phase, cosmologists eagerly anticipate the new insights that will emerge, whether unraveling the mysteries of dark matter and dark energy, understanding galaxy formation, or searching for life beyond Earth. The telescope stands at the forefront, poised to change our view of the universe in ways we never imagined. In conclusion, the intersection of cutting-edge technology, theoretical development, and precise observation heralds an exciting new era for cosmology and astronomy. James Webb's contributions are set to play a critical role in refining our understanding of the universe's origins and evolution, introducing new challenges to established theories, while simultaneously opening doors to revolutionary discoveries. As we venture deeper into this exploration, the mysteries of the universe await, with the James Webb Space Telescope leading the way in uncovering the secrets of our cosmic legacy and future. The impact of the James Webb Space Telescope, JWST, goes beyond measuring the expansion of the universe or revealing the details of early galaxies. It is also poised to address some of the most significant questions of cosmology. That our current understanding of the universe may be fundamentally flawed is not a new one, but the accuracy of JWST observations has brought this possibility into sharp focus. This includes understanding the behavior of dark matter and dark energy, which are key to the universe's large-scale structure but remain elusive. One of the most intriguing aspects of JWST's potential lies in its ability to study the early universe in ways that past telescopes such as Hubble could not. With its capacity to capture light from galaxies formed only 300 million years after the Big Bang, JWST is providing insights into the earliest stages of galaxy formation. The existence of massive, mature galaxies at such an early point in the universe challenges the conventional theory that galaxies should have taken longer to form. This raises the possibility that certain processes, such as star formation or black hole growth, may have been much more efficient in the early universe than we thought. Moreover, these unexpected discoveries have implications for galaxy formation, as well as for understanding the role of dark matter in shaping the universe's structure. Dark matter is believed to have played a crucial role in the formation of galaxies by exerting gravitational forces, but its precise nature remains a mystery. JWST's observations could help illuminate how dark matter influenced galaxy formation, potentially uncovering new properties of this elusive substance. In addition to dark matter, JWST is also supporting the study of exoplanets and the conditions necessary for life beyond Earth. One of the telescope's key missions is to analyze the atmospheres of distant exoplanets, searching for signs that could indicate habitability or even life. By studying the chemical composition of exoplanetary atmospheres, scientists hope to uncover the conditions under which life could arise elsewhere in the universe. These discoveries could offer valuable insights into whether Earth-like conditions are rare or common across the cosmos. As we delve deeper into the data from JWST, it is becoming increasingly clear that we are on the verge of discovering new physics. Whether it's the mystery of dark energy's evolving nature, the surprising complexity of early galaxies, or the elusive behavior of dark matter, JWST is opening up new avenues for understanding the universe. It is not only refining our current theories but also challenging them, forcing scientists to think in new ways and reconsider how likely it is that some of our most fundamental assumptions may need to be revised. Furthermore, these discoveries are advancing our knowledge of cosmology, as well as pushing the boundaries of particle physics, stargazing, and even philosophy. As we continue to explore the universe from the perspective of JWST, we are not just learning about stars and galaxies, we are gaining a deeper understanding of the fundamental laws of physics that govern our existence. The questions raised by JWST's discoveries could lead to a paradigm shift in how we understand the universe's origin, its structure, and its ultimate fate. As the James Webb Space Telescope continues its mission, it is poised to provide answers to questions that have long eluded us. Its capabilities offer astronomers the unique opportunity to peer into the early universe, where the seeds of galaxies, stars, and even life were planted. By examining the faintest and most distant objects in the cosmos, JWST promises to reveal new insights into the evolution of the universe, its structure, and its underlying forces. In particular, the telescope's ability to observe exoplanets in detail is one of its most promising features. By analyzing their atmospheres, JWST will help determine whether conditions suitable for life exist elsewhere in the galaxy. This is one of the most profound questions of modern science. Are we alone in the universe? The data gathered from these distant worlds could provide the first clues that Earth-like planets are common in the universe, expanding our understanding of where life might exist beyond our planet. Furthermore, JWST will help scientists understand the forces driving the universe's accelerated expansion, particularly the enigmatic role of dark energy. As it studies distant supernovae and galaxy clusters, JWST will contribute to refining our models of cosmic evolution. Its high-resolution imaging will allow for a better understanding of how dark matter and dark energy shape the universe on both small and large scales. On a deeper level, the observations made by JWST could also help answer fundamental questions about the laws of physics. By revealing details about the very early universe, where quantum effects and the behavior of gravity are intertwined, JWST has the potential to offer new perspectives on the nature of space, time, and matter. As we peer into these cosmic relics, scientists may discover phenomena that challenge our current understanding of physics and lead to revolutionary breakthroughs in fields such as quantum gravity or high-energy particle physics. The collaboration between observational and theoretical scientists will play a crucial role in interpreting the wealth of data expected from JWST. New theories and models will need to be developed to explain these discoveries, and as we push the boundaries of our knowledge, the lines between cosmology, physics, and other fields of science will continue to blur. The James Webb Space Telescope is more than just a tool for exploring distant galaxies or the search for exoplanets. It is the gateway to a new era in astronomy and cosmology, one where the mysteries of the universe can be explored in ways that were once thought impossible. As we move forward, the discoveries made by JWST will shape the future of science, offering answers to questions that have captivated humanity for millennia. In the grandest sense, JWST is providing a view into the universe as it was just after the Big Bang, offering a glimpse into the earliest moments of cosmic history, when the universe was still in its infancy. By studying the first galaxies and stars, scientists can begin to understand the origins of the cosmos and the processes that led to the creation of the elements, stars, and structures we see today. As JWST embarks on its mission, the excitement and anticipation among the scientific community are palpable. The telescope's discoveries are not only pushing the boundaries of our knowledge, but they are also changing the way we view our place in the universe. Each new breakthrough brings us closer to answering some of the deepest and most profound questions about existence itself. The future of space exploration, cosmology, and our understanding of the universe lies in the hands of the James Webb Space Telescope.